The paradox is that at the atomic level, everything looks completely different. It turns out that the vast majority of matter is empty space. There are disproportionately large distances between atoms. If an atom were the size of a ball, the distance to the next ball would be comparable to the length of a football field. It turns out that everything we are made of hardly exists in the usual sense of the word. But if there really is emptiness between atoms, why do we feel solidity when we touch objects? Why do bricks hold up walls and bones hold up the body? Why is emptiness not chaotic chaos, but a solid foundation of matter? Today we will try to figure out what is really hidden between atoms. We will look where the ordinary eye can never reach. This is not just a matter of scientific curiosity. It is one of the most underrated mysteries of physical reality. And as is often the case in science, the more we learn, the more we are amazed. When we look at any surface, be it a piece of metal or even our own skin, it seems to us to be solid, monolithic, as if there were not the slightest gap between the particles. But if our eyes could zoom in on the image as much as a powerful electron microscope, we would be shocked. The material world would turn out to be as full of holes as a sieve. At the molecular level, even the densest materials resemble tiny planetary systems scattered in a void. Atoms are a nucleus in the center and light, almost ghostly clouds of electrons around it. But between them is a distance hundreds of thousands of times greater than the size of the nuclei themselves. For example, if the nucleus of an atom is enlarged to the size of a grape, the electron will revolve at a distance of about 100 meters, and there will be literally nothing between them. High-resolution electron microscopy has confirmed this visually. In images of a crystal lattice, you can see orderly rows of atoms in the emptiness between them. The higher the resolution, the more obvious it is. Hardness does not come from density, but from interaction. Atoms seem to hang in space, held in place not because they touch each other, but because powerful forces of repulsion and attraction act between them. A visual and tactile deception comes into play. We think that materials are dense because atoms do not allow other atoms to pass through them. But in fact, this is just an illusion of continuity caused by the electromagnetic forces between atoms, preventing them from coming too close together. When you touch a wall, your atoms never actually touch its atoms. They simply begin to repel each other before that happens, creating a feeling of solidity. Now imagine that everything you thought was solid and reliable is actually mostly empty space. And this is a scientific fact verified by the most modern instruments. So every time you touch something solid, know that you are touching empty space held together by invisible laws of nature. The fact that there is supposedly emptiness between atoms is only half the story. The other half is much more interesting. What keeps these atoms in place? Why don't they stick together into a shapeless mush and fly off in different directions like dust in the wind? Each atom is not a compact ball, but rather an energetic structure. At the center is a heavy nucleus, surrounded by a so-called electron cloud. It is called a cloud because, according to quantum mechanics, electrons do not revolve in orbits like planets, but rather spread out in a probability space, forming a blurred zone where they can be found. These clouds are the true masters of interatomic space. When two atoms approach each other, their electron clouds begin to overlap. And this is where one of the strangest and most powerful rules of the quantum world, the Pauli principle, comes into play. It states, two electrons cannot be in the same quantum state. It's as if in a huge library, each reader could only sit in a unique chair with unique lighting, and God forbid anyone tries to take the same seat. The electrons get upset and start pushing each other, creating a repulsive force that prevents the atoms from getting too close. Here's a simple but striking example. Try taking two pieces of chalk and pressing them hard against each other. You will feel hardness, resistance. Logical. But if you could turn off the electromagnetic forces that hold electrons together, you would simply push one piece through the other, as if through smoke. All the hardness is an illusion caused by the mutual repulsion of electron clouds that do not want to share space. But that's not all. Coulomb force. The electrostatic repulsion between negatively charged electrons amplifies the effect. Even if there were no Pauli principle, the charges themselves would repel each other. This results in a double barrier. physical and quantum. Now imagine an architectural marvel built without scaffolding, without bricks, only from invisible forces. This is exactly how everything we see around us is arranged. Matter is held together not because atoms touch each other, but because they refuse to come close. If it were possible to turn off the electron clouds, matter would cease to exist as such. Everything would crumble into nothingness, because it is the electron forces that create what we call form, solidity, and volume. Electrons, which have a mass a million times smaller than that of the nucleus, form the basis of the stability of the entire material world. Tiny, ghostly particles that never touch each other directly create an invisible but unyielding structure that holds everything together, from the table in your room to the stars in the sky. At first glance, there is simply emptiness between atoms. But this view is mistaken. It is not a lifeless void, but a dense, highly active energy field. It is this field that binds atoms and molecules together, molecules into materials, and materials into the world we know. And this is not philosophy, but quantum physics in its purest form. Between each atom, there is a set of interaction forces that can be compared to stretched invisible threads. These threads are not just abstractions, they are electromagnetic fields, the exchange of virtual photons, and in some cases even the so-called van der Waals forces. They are born as a result of electron vibrations. And it is these microscopic jolts that translate into the macroscopic stability of the material. To understand this in some way, imagine a lattice of atoms in a crystal. Between them is not nothing, but a pulsating web of fields, in which each oscillation of one atom instantly affects the connection. This web acts as an energy framework. It determines how strong a metal is, how plastic bends, why ice is slippery, and why glass is fragile. We perceive the properties of a material, but in reality we are interacting with the energy between atoms. The coolest thing is that this energy connection is never static. Even in the most ideal crystal lattice, there are so-called zero-point fluctuations, which never disappear even at absolute zero. This means that even in calm matter, invisible energy is always bubbling. The vacuum between atoms is not empty at all. It hums, pulsates, and vibrates. Here is an interesting example. In 2023, a team of physicists from MIT conducted an experiment observing the behavior of phonons, quasi-particles that are tiny elastic waves in a crystal lattice. They saw that phonons arising inside a crystal propagate precisely because of this energy structure between atoms. Without this framework, the phonons would simply have nowhere to transmit their vibrations. And here's the paradox. The closer you look at matter, the less substance there is and the more energy there is. Where we expected emptiness, we discover nature's invisible engineering network, where everything is held together not by contact, but by fields and principles of interaction. At first glance, it seems that the atoms in a material are arranged in a strict and precise manner, especially in crystals, where they are arranged in perfect geometric patterns. But this order is an illusion of stability, sustained by the eternal struggle between the forces of attraction and repulsion. It is not a concrete foundation, but rather a rope stretched over an abyss. It fluctuates slightly all the time, but does not break. At the atomic level, nothing is at rest. Every atom vibrates, and it does so continuously. Why? Because its position is not a point on a map, but a probability cloud determined by the laws of quantum mechanics. It may be mostly in the center, but it constantly wobbles within an acceptable range. And this is not chaos. It is quantum order, in which motion is built into the very structure of the world. The most interesting part begins when we consider interatomic distances. For example, in a silicon crystal, the average distance between neighboring atoms is about 0.2 nanometers. It would seem to be dense, but let's compare it to the diameter of the atom itself. It is about 0.1 nanometers. That is, there is a space between them that is almost equal to their own size, which resembles a dense but still porous lattice. Now pay attention to what happens if one atom accidentally moves a little further than usual, or conversely, moves closer. In the macroscopic world, this would be insignificant, but in the world of atoms, it can cause local instability. One failure and the domino effect begins. Recall, for example, how melting occurs. Atoms vibrate intensely, disrupting their average positions until the entire lattice collapses. The transition from solid to liquid is not a destruction of bonds, but a loss of collective order between atoms. Here's an interesting example. Imagine an ensemble of hundreds of accordions playing the same note. This is a stable, solid body, but as soon as one starts to play out of tune, the whole harmony collapses. And if everyone starts playing at their own pace, it's chaos, analogous to a molten state. Matter works the same way. The stability of interatomic distances is music that nature has been playing for billions of years. But the most incredible thing is that this order is not rigid, but dynamic. It is maintained not by external forces, but by the atoms themselves, which are constantly bargaining between the convergence of attraction and the divergence of repulsion. It's like a crowd in a square where no one touches anyone else, but everyone maintains a comfortable distance. Even ultra-precise quantum simulations confirm this behavior. Scientists, modeling the behavior of individual atoms on supercomputers, find that order is maintained only if atoms are allowed to oscillate. Paradoxical, but true. A little chaos is a prerequisite for stable order. Contrary to common sense, most of the space in a solid body is nothing. Emptiness, a vacuum. If we take, say, a cube of iron and try to see its structure under a super-powerful electron microscope, we will find not a dense mass, but a lattice where atoms hang at a distance from each other, like light bulbs in a garland. But we already know this, as I have already talked about it earlier. But where does mass come from? Hardness, elasticity, and most importantly, how can you compress something that is already almost empty? The answer lies in invisible forces and quantum effects that literally support matter from within. There is indeed a lot of empty space between atoms, but this space is not passive. It is filled with electromagnetic fields, quantum fluctuations, and resistance, which begins to manifest as soon as you try to compress the material. Try squeezing a metal ball. At first it's easy, it bends slightly, the atoms move a little closer together, but then you increase the pressure, and that's when the real physical resistance begins. Why? Because as they move closer together, the electron clouds of the atoms begin to repel each other, as if you were trying to bring together two identical poles of a magnet. The closer they get, the stronger the repulsion. Two electrons with identical quantum numbers cannot exist in the same state, which means that matter resists compression, even if it seems that you are compressing a vacuum. In laboratories, scientists have learned to compress materials to extreme densities using diamond anvils, creating pressures of millions of atmospheres. For example, under such conditions, ordinary hydrogen turns into metallic hydrogen from gas. Its atoms are compressed so closely that they begin to behave like free electrons in metal. Now let's scale this up to cosmic proportions. Inside Jupiter, under tremendous pressure, hydrogen is in precisely this metallic state. Another interesting example is neutron stars. There, all matter is compressed to such an extent that there is no space between atoms at all. The electrons themselves are pressed into protons, turning them into neutrons. This is no longer matter but quantum madness, compressed to the limit, literally. Interestingly, even temperature affects how we perceive the empty space between atoms. When heated, atoms begin to vibrate more strongly, the distance between them increases and the material expands. It would seem that the atoms are the same, but the density decreases. Why? Because the void between them becomes larger, and the entire structure seems to swell with energy. This is where the real paradox arises. We compress what is almost empty and heat what is 99% nothing, and we get tangible effects. What is between atoms is not emptiness in the usual sense. It is an active, interacting, resistant environment. In other words, it is possible to compress emptiness, but only if we remember that it is not empty at all. It is a quantum arena where a whole arsenal of forces, constraints, and laws are at work, and everything we perceive as density is the result of an invisible struggle between energy and distance. At first glance, a vacuum is emptiness. No particles, no light, no matter. But at the quantum level, even this emptiness turns into a seething ocean of energy where virtual particles are endlessly born and disappear. Scientists call this phenomenon quantum fluctuations, and it is, without exaggeration, one of the craziest concepts in modern physics. In essence, a vacuum is not the absence of everything, but the basic state of the quantum field. Imagine that the entire universe is a stage, and fields are its foundation. Atoms, particles, energy are just waves on this stage. When nothing is happening, the field is still there. Moreover, it pulsates like a string, vibrating slightly even if you don't touch it. Some scientists believe that interatomic space is not nothing at all, but something like an active fabric of reality, where fields interact and change at the microscopic level. This fabric, in theory, can be even denser than any substance known to us, but not in the usual sense, but energetically. This is the quantum vacuum. Now let's discuss a more exotic hypothesis, string theory. According to this theory, all particles are not point objects, but tiny vibrating strings. And here's the most interesting part. Interatomic space can be an arena where these strings resonate, collide, tie themselves into knots, and untangle. What we call emptiness in this model is an active multi-level space where each vacuum is not an empty place, but a set of potential states of matter and energy. Just one change in the vibration of a string, and you no longer have an electron, but a quark. Some go even further. For example, the idea of vacuum energy or dark energy suggests that it is this background quantum nothingness that is responsible for the expansion of the universe. That is, what we do not see between atoms is not just a part of matter, but possibly a mechanism that controls the entire universe on a large scale. What if the vacuum is the basis of everything, and what we consider matter is just temporary bursts on its surface? In essence, the entire universe may be a flash of energy within some deeper quantum nothingness. Paradoxically, physicists are now studying the vacuum more actively than ever before. Various experiments, observations of fluctuations in the cosmic microwave background, and attempts to detect traces of supersymmetric particles all point to the fact that the vacuum is not only real, but also incredibly complex. We started with a simple question: what is between atoms? And the further we went, the clearer it became that there is no single simple answer. Instead, there is a whole mosaic of interactions, forces, fields, and hypotheses. It all starts with an optical illusion. Our eyes see solid objects, although at the atomic level it is a lattice with huge gaps. Then we discover that even these gaps are permeated by electron clouds, electromagnetic forces, and repulsion generated by the very nature of particles. Compressing them does not simply mean removing nothingness. It means entering into a battle with quantum laws. We have learned that there are extremely precise interatomic distances between atoms, not the edges of perfect chaos, and that these gaps are not subject to chance, but to strict mathematics. We have seen how even temperature and pressure play with these distances, distorting, compressing, and expanding them, forcing matter to play on a quantum piano. But the most amazing thing begins when we dive into the hypotheses of the quantum vacuum, a roaring void where something appears out of nothing and disappears back into nothing, where energy exists even where there seems to be no particles at all. String theory, fields, virtual particles, dark energy. All of this points to the fact that between atoms, there may be not nothing, but the source of everything. In other words, in every tiny gap between atoms, there is not emptiness, but potential. Potential for matter, for energy, for the very structure of space and time. We are used to thinking that the universe is a collection of objects, but perhaps it would be much more accurate to say that the universe is a collection of relationships between them. And the emptiness between atoms is what connects them.